5 today, it's a pretty fun one. So really what we've kind of been looking at with the last several units, Unit 1 kind of being the exception, funny enough, but mostly with the last several units has been establishing a background so that we can do what we are going to start doing in Unit 5 and then ultimately in Unit 6 as well, which is to like do statistics with the stuff that we are actually working with. Today we're going to be defining what is called a probability distribution function. I'm going to often abbreviate that as a PDF. Before we can talk about PDFs, though, we are going to first start by talking about what I find hilariously named the random variable, which is funny because it is written like a variable. You'll often see these denoted with like capital X's or capital Y's, and it is not a variable. Which is entertaining. These are going to be essentially functions that allow us to process outcomes into something that is actually workable. So for our definition here, we can think of this as a function that takes an outcome and processes it, whatever that means, into some number. Okay, what on earth do I mean by this? Taking a look at an example here. Let's say, for instance, that the event that we are doing is we are flipping 3 coins. And we're looking at all possible outcomes that we could see for flipping 3 coins. What is an example of an outcome that I could get by flipping 3 coins? Heads, heads, heads. Fantastic. So the outcomes themselves are not particularly friendly to be used. They're kind of a little bit strange, and often what we will want to do is take an outcome and gain some valuable information from that particular outcome. So for instance, what might be something that we'd be interested in knowing about from those 3 coin flips? What might be of interest to us here? I'm flipping 3 coins, I get heads, heads, heads. But how could I maybe process that into something that's usable? What might be a feature of that outcome that I care about? I have confidence in us. What might we look for? I want everyone but Thomas, because Thomas has already had to sit through this lecture once. That's a great start. What is a feature of this outcome that we might want to talk about? So we're just trying to take our outcome and process. We'll introduce probability to it later.
What do you mean? Like in what sense? Talk about it.
I mean, just like what's an aspect of this outcome? What's like something that we could say about this outcome?
They're all the same.
Okay, so we could say that they're all the same. Maybe we could like look at the number of heads that we see from a particular outcome. Right? So for instance, if we had gotten instead something like tails, heads, tails, We could talk about a different number of heads, or we could talk about what's going on in like tails, tails, heads, also a different outcome, but maybe share that feature with one another. So the random variable is going to be a function that takes in an outcome and converts it into that particular numeric value. So for instance, let's define our random variable, this is a capital X, as being the number of heads in an outcome. What is going to be the value that this random variable takes on when considering the outcome heads, heads, heads? 3. Okay. What is the value that this variable is going to take on, that this random variable is going to take on when it processes the outcome of tails, heads, tails? 1. And what is the value that it will take on when it's processing the outcome of tails, tails, heads? Also 1. So it's a way for us to take this kind of unpurified, difficult to work with outcome, which is heads, 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 3 H's in a row, and process it into something a little bit more usable. We have 3 heads, or we have 2 heads, or we have 1 heads, whatever, 0 heads. Okay. We could have also defined a random variable that looked at number of tails and run each of our outcomes through that random variable, and you'd get different numbers. And that's okay. And you'd have different values for different random variables. You might even have different probabilities for different random variables. Totally, totally fine. We could look at another one. For instance, let's say maybe that we're like rolling 2 dice. And maybe we define the random variable y to be the sum of the 2 dice. This is something that we've looked at before. What is going to be the value that I get for my random variable when I see an outcome like this? Yeah, it's 5. Okay, what is going to be the value of my random variable if I see an outcome like, it's not my best die in the world, say something like this, something like this. What's my outcome going to be? That is my outcome. And then what is my random variable going to be? My random variable takes that outcome and turns it into 8. So taking the thing that we are working with, the actual outcome, and converting it into some kind of number to work with. All right, questions about our initial definition of what is a random variable? Also want to be clear of our function notation, because we haven't talked a lot about functions in this class, but we are not multiplying x by heads, heads, heads. We are taking the machine that is x, and we are running heads, heads, heads through that machine, and it is processing it and spitting out 3. Right, so this is our input, and it spits out number of heads that we have for that particular outcome. Okay. When we are talking about this, it's actually going to be fairly important that we make this distinction. We'll have some scenarios where what we are looking at are discrete random variables, and we will have some where what we are looking at are continuous random variables, and we actually handle them very differently. We kind of are pigeonholed into handling the continuous ones very differently, because otherwise we would not be able to make any headway. We've already looked at the difference between like discrete versus continuous. Can anyone remind me what it meant to be discrete versus what it means to be continuous? Yeah. Yeah, so discrete was like we had a set number of numbers that we could occupy. and continuous was anything from start to finish we could be. I like to think of this a lot. This is the kind of analogy that I have fallen on. If you think of starting at a particular value and working your way to a different value, a continuous variable is one where as you move from start to finish, you're going to occupy every single value in between. So the example that I like to use is for height. If I first measure someone as being 4 feet tall and then measure them later as being 6 feet tall, I know for a fact that at some point along the way, they were 5 feet tall. But more than that, I also know that at some point along the way, they were 4.5 feet tall. And I also know that at some point along the way, they were 4.95623182765 feet tall. Every single value in between start to finish, at some point we had to occupy in order to get to where we are. Similar with time, right? If I start running at 0 minutes, 0 seconds, and it takes me a minute to get all the way around the classroom, then at some point there had been a particular amount of time. Right? Every single instance of time that can fall between 0 and a minute, I had to have been existing in that particular moment. So a discrete variable is going to be a random variable that can only take on, I like the way Liz described it here, can only take on specific values over an interval. Another way to think about that is there are going to be gaps between the values. Whereas a continuous variable is going to be a random variable. So RV denotes random variable that can take on any value over an interval. So there are no gaps. All right, let's take a moment, take like a minute, looking at the examples that we have here. So we have a bunch of potential random variables, and we are going to try and figure out if what we are looking at is a discrete case or if it is a continuous case. So yeah, take a minute, label these as discrete or continuous. We'll go over them here in a second. All right. So starting off here, number of books in a university library. What did we say for this? This is going to be discrete. If I start with 500 books and then I go from 500 books to 501 books, was there some point where I had 500.4 books? No, that doesn't make sense, right? Because we can't have a fourth of a book or 40% of a book. Right, so there are values in between our possible values that that this can occupy. Thomas, can you run to Miss Biddick real quick?
Oh, yeah.
Yeah, cool. Awesome. Okay, the amount of time it takes to get to work. What did we say here? Continuous. If it takes me 0 minutes versus if it takes me 10 minutes, then at some point in my travel, I have passed through every single possible time in between those two values. Right? I think I'm smoothly increasing from start to finish. I don't skip over, right? I don't just immediately teleport second by second by second by second. We're not glitching through time. Okay. Volume of blood drawn for a blood test. Continuous. Think about like literally the thing filling up as we go. It's not like it just increases. It's a gradual kind of filling up. We occupy every single value between 0 and whatever our endpoint is. Number of tornadoes in May. Discrete. Can't have a fraction of a tornado, but even if we couldn't have like an irrational number. We couldn't have pi tornadoes happening in May. Right? That wouldn't make sense. Exact amount of snow on Christmas is going to be continuous if we think of starting at no snow and then working our way up to however much snow we have to pass through every single height of snow, every single amount of snow on our way there. I guess technically it's a discrete process because we have these individual snowflakes that are technically piling up. It is close enough to continuous that we will call it continuous. And then the amount of snow on Christmas, if we are taking that and rounding it to the nearest 10th. This one's tricky. This is going to be discrete. Now, this one is tricky because the amount of snow we said is continuous, right? There's not a reason why we couldn't see a particular amount of snow. The issue is we are trying to describe the values that our random variable is allowed to be. So for instance, it is entirely possible to see 10.05 inches of snow. That's possible, right? But what is our random variable going to read as if we saw 10.5 inches or 10.05 inches? This is going to be reading it as 10.1. Right? So it can never actually occupy this value of 10.05, even though that might be the true height. Right? But our random variable is instead going to have gaps. It's going to go straight from 10.1 to 10.2, from 10.2 to 10.3 to 10.4. It's never going to occupy that space in the middle, even though the true height could be occupying that space. So a little bit of a tricky one there at the end, but hopefully it makes sense why the variable itself would be discrete, even though the data is continuous. How are we feeling with our continuous versus discrete? This was a tricky thing from Unit 2 that a lot of people struggled with, but hopefully it is making more sense now. Feel good? Not too horrible? So unspeakably horrible that, you know, talking about it is gonna cause our skin to slough off or something like that. Man, we are tired today. We are not awake. And that's such a shame. We have so much fun things to talk about. This is the like exciting part of statistics. Okay. Probability distribution functions. These are at their core somewhat annoying to fully define. We're going to look at an example first, and then we're going to take that example and use it to kind of generate a distribution, a definition. Ultimately, what we are looking at here, we have our random variable, which is a function that is going to take in an outcome, and it's going to process it into a number. We then have a probability distribution function, which is going to take in that processed number, that random variable, and is going to spit out some kind of likelihood for seeing that particular value. So this is like function composition. We have a function inside of a function that inner function is taking in outputs, and ultimately we are looking at probabilities here. Let's consider, again, a discrete probability distribution function for the likelihood of tossing 3 coins and getting certain results. For all of these PDFs, we're going to need a random variable to work with. We need like a condition to measure. If we're just tossing coins, then there's not really a thing to measure. So let's use the one that we defined earlier. We said that our X was equal to the number of heads. Sure. All right. So X is number of heads. We need to, for this, examine every single possible outcome. So let's go through this methodically. What are all of the possible results that I could see, all the possible outcomes for tossing 3 coins? Heads, heads, heads. Sure. Tails, tails, tails. Tails, heads, tails. Heads, tails, heads. Okay. Heads, heads, tails. Tails, heads, heads. Cool. 2 more. Tails. Yeah, tails, tails, heads. And last one. Heads. Heads, heads, tails we already have, but I think heads, tails, tails we don't have. So 8 total options. We want to apply our random variable to each of these outcomes. So for instance, what is our random variable going to be if we see the outcome of heads, heads, heads? 3. What is it going to be if we see the outcome of tails, tails, tails? 0. What is it going to be if we see the outcome of tails, heads, tails? 1. Heads, tails, heads, it's going to be 2. Heads, heads, tails. 2. Tails, heads, heads. 2. Tails, tails, heads. And heads, tails, tails. Okay. So that's just our random variable. That's all possible values of our random variable given our outcomes that we could see. So that's the first layer of processing. The next is to take that random variable information and convert it into a probability. So what are we going to look at here? Well, we're looking at the probability that our random variable is a particular value. So for instance, what is the likelihood that our random variable is equal to 0? This is 1 out of 8. Now let's translate this into context. The probability that the random variable is 0 is the same as looking at what? The probability that what is going on? So that's the outcome that it attaches to. But what does it mean for the random variable to be 0? No heads. This is the chance of not getting a single heads toss. Okay. What is the probability of our random variable being equal to 1 going to be? 3 of the 8. What is that kind of equivalent to saying? So our random variable is 1 3 times. So 3 of the 8 possible values for what our random variable could be. What is the probability that we get 2 heads or that our random variable is equal to 2? 3 out of 8. And then the probability that we get all heads or that our random variable is equal to 3? Also 1 out of 8. This whatever. That's the PDF. No, that is just the PDF for this particular situation. We're not talking about binomial or anything like that. Yes. Yeah, we'll look at specific probability distribution functions later on in this chapter, and we'll talk about binomial distribution then. But this is just the PDF for this particular scenario. Now, this strategy of going through every single possible outcome and looking at the number of times a particular value of our random variable shows up can only work if it's discrete. Why wouldn't this work if we were dealing with a continuous variable? What's the issue? If this were a continuous variable instead, how many different outcomes would we have to work through? Continuous variable instead of discrete, how many outcomes would we have to work through? Infinity. We'd have to work through an infinite number of outcomes in order to be able to do this. We can't work through an infinite number of outcomes. So it being discrete is important for us to know so that we don't try and go ahead and do this for what we have. We'll have a different set of tools that we use for our continuous probability distribution functions. But for our discrete, notice that what we are doing here, this is a function which we will define of x at a particular value of x. This is our random variable at a value. Which tells us, which gives the probability that our random variable is the specified value. All right, so if we're looking for the probability that our random variable is equal to 1, then we look at every single case in which our random variable is 1, bam, we find that probability. Easy peasy. Should we take a look at another example? Do we have any questions that we want to address from this one? Or should we look at another? Feeling okay? Cool. Let's take a look at another example. We're trying to figure out the PDF for rolling a balanced die. So we'll assume we're not cheating, right? All of the sides are equally likely. We have to deal with it in a slightly more complicated way if that's not the case. Before we construct a probability distribution function, we need to assign a random variable. So this is going to be some kind of thing that talks about some feature of the outcomes that we are going to be getting. What are our possible outcomes here? Rolling a die. 1, 2, 3, 4, 5, 6 are our possible outcomes. What's maybe a feature of these outcomes that we could talk about with our random variable? Any ideas? How about if we get a number that's like greater than 2 or something? Right? Maybe we want to define whether or not the number is greater than 2. So if we want y to define that, we'll say the random variable y. We've already used x, so we'll use y here. We'll say the random variable y. We want it to say that this should be defining the if the number is greater than 2. Sure. Now, this is a yes or no question, right? It's either yes, it is greater than 2, or no, it is not greater than 2. So it's not going to, as it is right now, spit out a number. What's maybe a way that I could communicate numerically that yes, it is in fact greater than 2? What number could I ascribe to represent yes? Sure, we could do 0 or 1. Generally speaking, what would 0 represent? No, and 1 would represent yes. That's a fine way to do it. So maybe our random variable will be 0 if it is less than or equal to 2, and it will be 1 if it is greater than 2. Which is just essentially our way of saying yes or no, right? So if it's 1, that means yes. If it's 0, that means no. What is then the value going to be of our random variable for the outcome of 1? It is going to be 0. Is it greater than 2? No. Therefore, our random variable is 0, to denote that no, it is in fact less than or equal to 2. What's our random variable going to be for 2? Also 0. Is 2 greater than 2? No. Therefore, 0. What's our random variable going to be for 3? 1, because that is true, that it is greater than 2. What's our random variable going to be for 4? 1, because that is a yes again. What is it going to be for 5? 1. And what's it going to be for 6? Another 1. Yeah, exactly. So if we want to know what is the likelihood that our value here is greater than 2. Well, how could we translate the idea that our outcome is greater than 2? What does our outcome greater than 2 mean in terms of our random variable? What is our random variable going to show us when the outcome is greater than 2? Well, that's not what the random variable will show. What does the random variable tell us? So what does the random variable, what is our random variable telling us? Our random variable only has 2 options. So if it's greater than 2, what does our random variable show us? How does our random variable indicate to us, hey, this number is greater than 2? It shows us a 1. So the probability that we are greater than 2 should be the same as the probability that our random variable is equal to 1. Right? 1 is just our random variable's way of flagging us and saying, hey, this number is greater than 2. 0 is our way of flagging us and saying, hey, this number is not greater than 2. All right, so what is the probability that our random variable is equal to 1? What is the probability that the random variable is equal to 1? 4 out of 6. Okay. What's the only other option for what our random variable could tell us? It's either telling us 1 for yes or 0 for no. So what's the probability that our random variable is telling us no? 2 out of 6. So a slightly more complicated one here, right? Where the number that we're looking at, the fact that the random variable is equal to 1, doesn't actually mean anything numerically, right? That's linguistic. That's saying, yes, in fact, it is greater than 2. Or no, in fact, it is not greater than 2. But it's a way to take that verbal idea, that linguistic idea, and convert it into a number that we can process. Which is kind of cool. Okay, if I look at every single possible outcome, right? If my random variable works for all of my outcomes, which it should, if it doesn't, then we have a problem with the way we have constructed our random variable. What should be true about the total of all of my probabilities at the end of it? I am going to start cold calling people. I am getting pretty frustrated that I am speaking to myself right now. No, you're good. I know that is not directed at you. It'll add up to, yeah, the numerator should add up to the denominator. In other words, the probability of all of these events should ultimately equal 1. They should add up to 1. All right. So interesting thing to note for our probability distribution function, the individual probabilities should add to 1. All right. Otherwise, there are outcomes that we've missed. Right? There are outcomes that we're not taking into account. Another thing to note is that each of the values that we're seeing for our probability distribution function is a probability. What are our values allowed to be if they're probabilities? What condition must they satisfy? They have to be between 0 and 1. So for any given value of our random variable, it needs to be sitting between 0 and 1. A way we could communicate that is that 0 needs to be less than or equal to the probability of our random variable at a particular value needs to be between 0 and 1 for all x. Which is just to say, getting a probability, getting an individual probability of 1.2 wouldn't make a lot of sense. That would be like saying our random variable is this value 120% of the time. Likewise, getting a probability of negative 0.4 doesn't make sense. That's like saying the likelihood of our random variable being this value, it happens about negative 40% of the time. Those don't make sense. Those don't have logic that fits with them. Okay, so let's take a look at a couple examples of functions, and let's determine if what we are seeing is in fact a probability distribution function. Now, I do want to take issue with the notation here. Technically speaking, this should be the probability that our random variable is equal to y, and then this should just be lowercase y. And you would look at like probability that our random variable is 1, probability that our random variable is 2, probability that our random variable is 3, right? The probability of 2 doesn't make sense. As far as just like the way that it is worded, it would be the probability that the random variable is 2, but whatever, who cares about my opinions? That's fine. We'll interpret it as that, though. Okay, so looking at this first example here, just starting off looking at my individual probabilities, are there any of these individual probabilities that don't really look like valid probabilities? Or do all of them fit the condition that I need to have a probability? Are any of them negative? No? Any of them greater than 1? No? So these would all work for probabilities, right? These all could be the probabilities. Okay, so then what's the other condition that we need to satisfy? They need to add up to 1. Okay, we could plug that into our calculator. Sure, it might take a little while because it's a bunch of fractions. We could also think of 1/4 as being like 4/16. And what would 1/8 be? 2/16, 1/16, and then like 9/16. 4 plus 2 plus 1 plus 9. 1 plus 9 is 10. 2 plus 4 is 6. So this would be 16 out of 16, which is equal to 1. And so does this fit the bill for a PDF? Yeah, this could be a PDF. All right, take a moment to try out 2, 3, and 4. Are these PDFs? And then why or why not?
Does the top
Go for
have
it.
anything to do with it?
Yeah, so the top is the possible values of our x, but those can be pretty arbitrary. So it'll depend on what the random variable is trying to say, what those values of x could be. So for instance, the fact that, yeah. So the fact that like the x for the third one starts at 2, that doesn't disqualify it from being a PDF. Those are kind of just arbitrary.
Yeah. I mean, I wasn't really looking at it.
Exactly. Yeah, you kind of can ignore them for the most part. Now we wouldn't want to see like, since it's a function, we wouldn't want like repeated values of x, but that's not something I'm going to throw at you. But that could certainly be problematic if we saw that. Okay, for number 2, what do we notice?
That's negative.
So if we look at the individual probabilities, 2 of them don't work. Which 2 don't work? First one and the second one. What's that? Yeah, because it's different reason why it doesn't work. Yeah. So the first one doesn't work because negative 100% doesn't make sense. Negative percentages don't happen. Second one doesn't work because 150% also doesn't make sense. All right. Do these add up to 1? Yeah, they do add up to 1. Does it matter? No. The fact that it's disqualified because of the individual probabilities Because those can't be probabilities, this can't be a PDF, even though the sum of all of the values is 1. So this is not a PDF. Okay. Looking at our third example, what do we notice? They don't add up to 1. Would the individual probabilities work as probabilities? Sure, why not? But the problem then is that they don't add up to 1. This would be 1.2, and that is an issue. So this is not a PDF. It needs to be adding up to 100%. And then what do we see with the fourth one? They all work individually. They all add up to 1. And so this one would be a probability distribution function. Now, I could give you this table. I could also give you a bunch of outcomes, and we could figure out these probabilities from those. Sometimes, though, these are actually going to be given to you as functions. So sometimes the probabilities are going to be really nice, and we'll be able to actually like plug in a value and see what the probability is at that particular point. That's going to be particularly useful for our continuous probability distributions. But we could do it with discrete as well. So for instance, here we are given equations that will give us the probabilities as we plug in points. And the question is, do they make a probability distribution function for the values of x for which they are defined? So for this first example, what is this going to look like? Well, we have 3 possible values of x, and we have a way to figure out the probability of that value of x theoretically if this is a PDF. So for instance, if we're looking for the probability that x is equal to 0.1, what would I do? Yeah, just add them together. This is 0.1, and we're told to take that value of x and add it with 0.1. If this is a PDF, this is saying that that happens about 20% of the time. If this is a PDF. If it's not, then that's not what it's saying. Okay. Let's consider our probability that x is 0.02. What is this going to look like? Yeah, plus 0.1. Exactly like before, we get 0.12. So if this is a PDF, that's saying that there's a 12% chance of this happening. And when x is equal to 0.04, exact same deal. Plugging it in, I get that this, if this is a PDF, tells us that this is happening about 14% of the time. So for these values of x for which it is defined, is this a PDF? No, why not? They don't add up to 1. All right, 0.2 plus 0.12 plus 0.14 adds up to 0.46, which is too small. And so this would not be a PDF. Okay. For our second example here, what is our probability if this is a PDF? When x equals 1, what are we going to see here? Oh, yeah. No, you're right. You're totally good. I'm sorry. I was slow to keep up. I thought you were doing the values of x there. Yeah, that's perfect. 1 plus 2 divided by 12, which is, you can write it as 0.25. I'm going to write it as 3 out of 12 just to make the addition here that we'll do in a moment easier. But 0.25 is perfect as well. What is the probability of our random variable being equal to 2? Very good. And the probability of our random variable being 3. And what do I notice? First of all, are each of these valid individual probabilities? Yeah, they're all positive. They're all less than 1. And what do they add up to? And so this is a PDF. 0.46 is the sum of all the probabilities, which is
Okay.
not 100%.
Right,
Yeah,
okay.
not 100%.
I was just thinking of it between something and something.
Yeah, so each individual needs to fit between, but then the sum needs to be 1. Yeah.
I forgot.
Yeah. All right, how are we feeling about our PDFs, our random variables, about all that fun stuff? Feeling okay? Good. All right, we have about 30 minutes left today. What we are going to do with the remaining 30 minutes is spend this time reviewing for the Unit 4 test that we have tomorrow. I am going to, I have most of your guys' quizzes graded. I'm going to finish up the ones that I haven't. I'm going to hand back the quizzes, and then I'm going to field any questions that we have about Unit 4. So what I would do in the meantime, look through your packet, look through your Pearsons, look through the 4143 quiz that you have, identify any questions that you would like to go over, and then we will review those together once you do. Yeah, go for it. Why it's not. Whatever.